the world of apply, remember, in the world of apply, there aren't any expressions. There's just values. So apply doesn't know anything about scheme notation. All it knows about is how to call a procedure. Well, as it turns out, there are two kinds of procedures. And they are primitive procedures, the ones that are built in to the interpreter, and procedures you create with lambda, including in the actual scheme lambdas that are hidden inside a define with parentheses around the name, and lambdas that are hidden inside let expressions, right? But one way or another, there's a lambda that makes the procedure. So if we come down here, oops. What do we do if it's a primitive procedure? Magic. We do magic. Primitive procedures happen by magic. What that means in a real scheme interpreter is that primitive procedures are little chunks of machine language code, things that have been compiled into the native language of the computer hardware that carry out whatever it is that the primitive is supposed to do. For our purposes, I put it as magic because what that means is we're not interested. We just don't know how primitives work. That's for another day. Okay? The interesting part of apply is what happens if it's a lambda-created procedure. Well, if it's a lambda-created procedure, it comes from a lambda expression which looks like lambda of x, y, z, I don't know, plus x times y, z. Okay? That's a lambda expression. And it has formal parameters, and it has a body. And we have selectors, formals and body, that pull out the formal parameters and the body of a procedure. Because when we evaluate this lambda expression, we're going to create an abstract data type procedure. And that abstract data type has formals and body as selectors. And the other thing that we have is actual argument values. And that's in args, which is the second argument to apply. Okay? So the substitution model of evaluation says substitute the formal parameter, substitute the actual argument values for the formal parameters in the body, and then evaluate the resulting expression. And that's what this says. Substitute here, this thing that takes three arguments, body of proc, formals of proc, and args. Suppose I say lambda of x plus x lambda x times x3 plus x5. Okay? Let's say I call this with the argument 10. Footnote. This is a really stupid way to write code. First of all, you shouldn't have a variable called x unless you're writing a program that's doing, graphing of functions, and you have an x this way and a y that way. Then you can get away with calling something x. But usually you should use meaningful variable names. And second of all, more important, if you have a lambda of x, you don't want to also have another lambda of x inside here. It's only going to confuse you. But let's try to unconfuse you by grabbing the yellow chalk that I see over here, bad planning for lecturing. So I'm calling this whole 3-line lambda expression with 10 as the actual argument. So we're going to substitute 10 for x in the body. What is the body of the lambda? It's this. That's the body. Okay. So I substitute this x with 10. I substitute this x with 10. What about this one and this one? Should I put 10s here? Should I say lambda of 10 times 10, 3? No. I certainly don't want to say lambda of 10. That's just nonsense already. But I don't want to substitute this one either. Because for this inner procedure call, here's its body. And what we're going to substitute into that body is the value of plus 10, 5. So this x is 15. Right? So we do 15 times 3 is 45, plus 10 is 55. That's the value of the expression. And when I did that first substitute into the yellow body, this x was what we call protected from substitution by this x. Okay? So the actual substitute function that we're going to look at in a little bit is a little more complicated. Having said all that, the next thing I want to say is don't put a lot of effort into learning how substitute works. Because in a couple of weeks, we're about to learn that scheme doesn't really work this way. That scheme doesn't really do evaluation by substitution. We're going to learn a more sophisticated thing called the environment model of evaluation, which is how scheme really works. Substitution model, it turns out, is adequate for functional programming, but it's not adequate for some other ways of programming. We'll talk about why that is later. For now, all I want to say is just, take on faith that substitute does the right thing. And don't get caught up in the code of it. But you should understand this line where the cursor is blinking, where we take the body of the procedure, and in that body, we replace each occurrence of a formal parameter with the corresponding actual argument value. Apply gets values. So there's no more expressions here when we're in apply, except for the expression that substitute returns. Okay, that's the expression that's this modified version of the procedure body in which we've substituted out the formal parameters and replaced them with the actual arguments. And we have to eval that expression, and that's what it means to call the procedure. So the line we were looking at before where eval calls apply, and this line right here where apply calls eval, these two things together are the heart of the interpreter. Okay, and they constitute a mutual recursion, and therefore a tree recursion. Now, what is it about scheme expressions that makes tree recursion make sense here? And tree recursion works for hierarchies, right? Two-dimensional hierarchies. We were talking about that this whole week. What's the hierarchy in a scheme expression? Well, scheme expressions can have sub-expressions, right? And those sub-expressions can have sub-expressions, and so on. So it's not surprising that there's a tree recursion involved in doing eval. And the other thing is, expressions can call procedures. Those procedures have bodies which are expressions. And so that also gives rise to mutual and therefore tree recursion.